Hi, good morning, everybody. Today we're going to be spending some time talking about acid-base neutralization reactions. While I'm going through this, you should probably have out your notebook and be prepared to take some notes as we go along. You, of course, can stop the video at any time so you can take some notes. I'm going to start with acid-base neutralization reactions where we ended with it in our sophomore year. And so first thing I'm going to do is I'm going to take a look here at what exactly it is. An acid-base reaction is really just a double replacement reaction that takes place, of course, between an acid and a base. And here the H plus ion, also known as the hydronium ion in the acid, reacts with the OH ion in the base. Ultimately, if we have a strong acid and a strong base reacting together, we'll end up with a pH of 7. So what is the overall molecular reaction for a acid-base reaction? There we have it. HA for the acid plus BOH for the base yields water and an ionic salt. Okay, so an example is given there where we have the molecular formula of hydrobromic acid reacting with some sodium hydroxide, forming the ionic salt called sodium bromide and some water. When we break these apart into their ions, with the only one not being broken apart into ions are pure liquids like water and gases like carbon dioxide. When we do this, we end up with H1 plus, Br1 minus, Na1 plus, and OH1 minus. And on the opposite side of the arrow, we end up with Na1 plus and Br1 minus. One of the things that you're going to notice is that in the net ionic equation, the Na and the Br are both taken out. And that is because the Na and the Br are both spectator ions. You notice that they do not change from the left to the right side of the equation. So those are called spectator ions. And so we take those out because they're not part of the chemical reaction, leaving only the net ionic equation, which is the only part that is part of the chemical reaction. So that's why, as you can see, this is why this is called a neutralization reaction, because what it makes is water, and water is neutral. We have another kind of acid-base reaction, and that kind of acid-base reaction is one in which a carbonate is the base. So we have HA for the acid, BCO3 for the carbonate base, and this time we're going to make water, some carbon dioxide, and the ionic salt. So that's the really only difference. The carbonate breaks down a bit into the carbon dioxide gas. So as you can see, we end up with our example, hydrochloric acid, reacting with sodium carbonate to form water, carbon dioxide, and the ionic salt, this time NaCl. So for the ionic equation, we break apart things that are soluble. So everything except water and the gas, CO2, are broken apart. And then what we end up doing is we end up canceling all of our spectators. So in this case, our two spectators are the sodium and the chlorine on each side. Those spectators are canceled out, and we are left, in fact, with our total overall reaction. Now, you'll notice that this reaction really needs to have a 2 here for it to be valid. And so that, therefore, once we have that 2 there, the charges will balance, 2 plus, 2 minus, and the H's will balance, 2 H1 plus, and the 2 H's on the inside of the water. If we look at our next example, you're going to start to notice a pattern that will emerge every time we do an acid with a hydroxide and every time we do an acid with a carbonate. So here we have sulfuric acid can be neutralized with potassium hydroxide. So we write out our molecular equation, sulfuric acid, potassium hydroxide. Yes, you are going to have to try to remember how to write these. Many times as you're going to see the IB will give you what the formulas are for sulfuric acid, and because they usually don't expect you to have to remember what the acid formulas are, but they would expect that you can write a potassium hydroxide reaction, and then you do have to be able to do that whole double replacement, A together with D and C together with B, to be able to figure out what the products are. Then we have to, of course, cancel out our spectators. Do you notice that I balanced this? Do you notice the 2 in front of the KOH and the 2 in front of the H2O? This is so that I can remember that I have to keep everything balanced. And then at the end, if you notice the net ionic equation, I end up being able to cancel all the 2's out because they're all the same on both sides. So I'm left with H1 plus OH1 minus yields water. And water, remember, does not get broken apart because it is a pure liquid. Okay, so let's go look at an example that contains a carbonate reaction. And so here we have lithium carbonate neutralizes nitric acid, and the molecular formula comes out as Li2CO3 because Li is 1 plus and CO3 is 2 minus. And then we have H2HNO3 yields 2 LiNO3. And once again, LiNO3, Li is 1 plus, NO3 is 1 minus. Discussing our charges, we end up with LiNO3 plus some water and some carbon dioxide. We do balance the equation, and then we go ahead and cancel out our spectators. So 2 Li1 plus is canceled, and the 2 NO3 1 minus is canceled, leaving us CO3 2 minus plus 2 H1 plus yields water, liquid, and CO2 gas. Okay, so I'd like to at this time have you try this one all by yourself. So if you would please stop and try this out, and then record your answer. This will be on this will actually be on the Ed puzzle. So please stop this right here, record your answer, and then let's see if you have gotten the right answer. Okay, so the correct answer for acetic acid neutralizes sodium hydroxide. We end up being able to write it out. CH3COOH plus NaOH yields CH3COO-Na. It doesn't matter what side you put the Na on, it does not matter at all, plus water. And so we get to cancel out our two CH3COO1 minuses. We get to cancel out our Na1 pluses, and we are left with H1 plus OH1 minus yields water. You should be starting to see a pattern here. Every time we have a hydroxide reacting with an acid, we are going to end up with H1 plus OH1 minus yields H2O and liquid water. Okay, let's go ahead and have you pause right here again. Answer the question, can you figure out what the correct net ionic equation will be for magnesium carbonate? So it is being used to neutralize hydrochloric acid. So go ahead and try that one out next. And you're going to record that in your Ed puzzle right now. Okay, so here we have magnesium carbonate written correctly as MgCO3 plus 2HCl, the 2 is for balancing, yields MgCl2 because we had an Mg2 plus and a Cl1 minus. Crisscrossing, we get MgCl2 plus some liquid water and some carbon dioxide gas. This time carbon dioxide, remember, comes from when we have a carbonate neutralization reaction. We're going to cancel out our spectators, so the Mg2 plus and the 2 Cl1 minuses, leaving us CO3 2 minus plus 2H1 plus yields water and carbon dioxide. Again, you should be starting to see a very definite pattern of what you get for an ionic compound when you have a carbonate base and what you get for a net ionic reaction when you have a hydroxide base. Okay, you're going to try this again on the next example. And the next example is going to be when phosphoric acid is neutralized with potassium hydroxide. Go ahead and pause right here. Write down you're probably going to be describing this in words, what the net ionic equation is for when phosphoric acid is neutralized with potassium hydroxide. Okay, so you'll notice right away that we end up with, again, look at that magic. It's exactly the same thing. H1 plus OH1 minus yields water. So every time we have a hydroxide neutralization, we end up with this reaction. So I bet you can already tell what the next answer is going to be. Here we have a calcium carbonate is used to neutralize nitric acid. So go ahead and stop this right here and see if you can remember what does this come out to. Please use your words to describe what the reaction of the net ionic reaction is. And big surprise, ta-da, 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 we end up with calcium carbonate neutralizing nitric acid to form just the exact same thing, CO2 minus, 2H1 plus, yields water, and carbon dioxide. Okay. The rest of this video is all about ID calculations. So you are going to be able to scroll through the rest of this video. I'm going to do this quickly because we have about 4 minutes left of time, and I'm going to try my best to talk about this. In the first one, you have a student determine the percentage of the active ingredient magnesium hydroxide, see there it's given to you, in a 1.24 gram antacid tablet. The antacid tablet is added to 50.00 centimeters cubed of 0.100 mole DM -3 sulfuric acid. So there you have a volume and a molarity. That's important because remember we use those two things to calculate moles. So ta-da, you are going to need to calculate moles. So it should not be a big surprise here what to do. I'm going to give you a chance to figure out how to calculate your moles right here. And we'll do the Edpuzzle thing where you fill in your answer. Okay, so we look at the number of moles of H2SO4. That gives us the liters. Notice that the 0.0500 DM3 is the conversion to liters times the molarity. So liters times the molarity gives us the number of moles. All right, the next one we're going on to is formulating the equation for H2SO4 with MgOH2. So you can go ahead and stop and use your words this time to describe what the reaction is going to be and what it will form. You may do this in the full molecular saying what the two products are that are formed. So ta-da, no big surprise there. H2SO4 and MgOH2 form magnesium sulfate and water. All right. So then we are going on to the next reaction, and this says excess sulfuric acid required 20.80 milliliters or centimeters cubed of that molarity of NaOH. Calculate the amount of excess acid present. By this I mean the amount of moles of excess acid present. So you're going to figure out how much was used up, since that was a 1-to-1 ratio. If you find out how much was used up by this reaction of NaOH, then you're going to find out how much acid was used, so you can subtract moles minus moles. And let's take a look at the mark scheme. So in this one, they are using, now why did they use 1/2? Let's go look at, was there a mole ratio here of 1/2? So I think you end up with half. No, I am seeing, why did they use half? Because the mole ratio is already balanced. Let's look here and see. So it's got 1/2 times the moles of NaOH and the moles of the, oh, because that's exactly half. That gives us exactly the half number of moles. So we'll go back and talk about this a little bit in our next video.